the Lagrangian and the Hamiltonian formulation of classical mechanics. We're going to discuss that as a prelude to the path integrals. So before we do that, let's just make some motivational comments. So what have we seen so far? So far, what we have seen is that quantum mechanics as formulated by many people were involved, but mainly Schrödinger, Dirac. So Schrödinger did the wave mechanics. Dirac found the more general linear algebraic formulation of it. We saw a little bit of the Heisenberg formulation, which is has to do with the operators. And then, there are other people involved, such as Max Born, the Born interpretation, and lots of other people. So in general, what we have seen is that we have seen what we could call wave mechanics, because that's based on some wave function, x psi of x of t, which is governed by the Schrödinger equation. Now, there is a related formulation, which is the Heisenberg formulation, Heisenberg's matrix mechanics. And what is matrix mechanics? It's basically, instead of the time dependence being contained in the wave function, it's contained in the operators, the observables, okay? The observables, and they become functions of time, and they satisfy an equation which is known as the Heisenberg equation of motion. And that equation is, it's unitarily equivalent to the wave mechanics. So these are unitarily equivalent. So if I ask you, what does it mean for two things to be unitarily equivalent, what would you say?
Same up to a unitary transformation.
Correct. Okay. So, but you see that in some sense, both of these, is related to a wave mechanics. But quantum mechanics is really about particles, right? So where do we see the particles? We see the particles when we observe them. We observe particles, right? And we've been told that when we are not observing the particles, they behave like waves. Otherwise, we would not be able to explain the double slit experiment, right? Because if the double slit experiment, it's the interference between the two waves coming in going through the two slits, which give us the interference pattern, and then we get a probability distribution from that, and then we see the particle distribution according to the probability distribution. Is that clear what I'm saying? Or should I explain it a little bit more in detail?
Sir, what are we talking about? I just came in, so.
We are talking about the formulation of quantum mechanics in terms of wave functions and how we only observe particles at the very end when we are doing the observations.
Oh, okay. Yeah.
So, we are told that we should not think of the particles in between observations, because in between observations, they're really, described by some wave function x of t, psi of x of t. But there is another formulation of quantum mechanics where even between observations, the particles can be described as particles. except that they are not classical particles. And that formulation is known as the path integral formulation. And this formulation was developed by Richard P. Feynman. And there's a very closely related development in statistical physics, or statistical in theory of random, in statistics, I should say, by Wiener. So they were almost parallelly, developed. Wiener worked on stochastic processes. Stochastic. So in the path integral formulation, we need to understand what the Lagrangian is. And so to really appreciate the path integral formulation, we need to understand the Lagrangian formulation of classical mechanics. Okay? So, and that is what we are going to be discussing today. So today we are going to be discussing the Lagrangian formulation of classical mechanics. Okay? Just as you can't really understand quantum mechanics without understanding the classical physics a little bit, similarly here. So I think for some people, or maybe for most people here, okay, I think Moon has dropped out because for whatever reason. But have you guys seen classical Lagrangian formulation of classical mechanics before?
Yes, sir.
Yes, sir.
In statistical physics class, right?
Yes.
Yeah.
Although I forgot most of the stuff, but I remember that. Yeah.
Okay. Did you guys learn it anywhere else, like in a classical physics in class or something?
Yeah,
Yeah,
in
in the
the
class.
classical mechanics course, it was also taught. Yeah.
Yeah.
Okay, good.
Last year.
So this is not new, but I'm going to start. I will assume that you don't really know much about it, because that way I can establish my own point of view and notation. Okay. So, the laws of physics, the classical laws of physics are usually formulated as differential equations, right? So the classical laws of physics are formulated usually in terms of differential equations, right? Perhaps the most famous of these is Newton's law, Newton's second law. Okay, so Newton's second law, what does it state? It says that the force on an object is proportional to its acceleration. So if the acceleration is a, and the proportionality constant is the inertial mass, then this is going to be given by the force. And the force we can write as minus the gradient of a potential, right? So this is the definition of a potential. Okay, so this is Newton's law. So another of my favorite classical law would be Maxwell's equations. So Maxwell's equations are, in the presence of sources, the divergence of the electric field is given by the charge density. So these are all local equations. You may have seen these equations, but in an integral form. But these are the differential form. And then the divergence of the magnetic field is 0. This is a statement that there is no magnetic monopole in the observable universe, or at least we have not found any. If you found magnetic monopole, we'd have to change the right-hand side of this equation. And then there is curl of B is, sorry, curl of E. Curl of E is given by minus the rate of change of the magnetic field with respect to time. And this is Faraday's law. Okay? And, or more appropriate, Faraday-Lenz's law. Because this minus sign is by Lenz. And this minus sign is very important, otherwise energy would not be conserved. And this equation is very, very useful because transformers are built out of the insight into this equation, right? Because or generators, for example, when we have in a like a hydroelectric generating station, the water basically spins around a loop of wire in a strong magnetic field. So the flux through the loop of wire changes. As a result, it creates an electromotive force, which we then use to run household objects. Anyway, so this, and then we have, sorry, I'm gonna stop getting sidetracked into fun physics. This is the Ampere's law, right? All right, so these are Maxwell's equations. So you can add your own favorite differential equation to this list. So, however, there exists an alternative, an alternative formulation of physics based on an integral principle. Okay. So not a differential principle, but an integral principle. But these two principles are equivalent. So you can derive one from the other, but you cannot derive either of them from more basic principles. So this principle is known as the principle of least action.